Lab 5 Falling Slinky. In Lab 5, we analyzed the motion of the falling slinky. We extracted position versus time data in Tracker and before constructing the theoretical model of the slinky in GlowScript. We then compared the theoretical and experimental models to see how accurate our model was. Concept used in this lab. Like previous labs, we use Newton's second law in this lab, where the final velocity of an object is equal to its initial velocity plus net force divided by mass times time. We see this in the equation form here as final velocity equal to initial velocity plus F net divided by mass times delta t. We also use the concept of drag, which is a force that acts in the opposite direction of an object's motion and is proportional to the square of its speed. This was necessary to do because the slinky is a falling object that had air resistance. Finally, we had to establish a unit vector for the motion of the slinky, which in our case was 0, 1, 0, since we needed it to point upwards. When we take a look at our code, we need to establish several important variables. We have the mass of the slinky as 0.25 kilograms, and we have the initial position vector, which was obtained from the tracker data, and the initial velocity vector as 0. The force due to gravity is 9.8, and the unit vector j hat is 0, 1, 0, as we discussed in the introduction. Next, we have the proportionality constant, which gives us a constant for the magnitude of the drag force. And this value is quite large because the video that we analyzed in Tracker was in slow motion. As we continue down, while the time is less than 5.44 seconds, we've established the weight of the slinky, as well as the force of tension and the net force. We also have Newton's second law, where the final velocity is equal to the initial velocity plus F net divided by the mass times the change in time, as well as the final position equal to initial position plus velocity times the change in time. Next, at this point of time is less than 8.32 seconds, we have established the drag force as Fd here in place of the tension, as we mentioned above, and we also have the weight of the slinky, and we'll discuss this in further detail later. And then again, we have Newton's second law applied here with the final velocity equal to the initial velocity plus F net divided by mass times the change in time, and final position is equal to initial position plus the ball's velocity times the change in time. When we look at the comparison between our data in Tracker and the data from GlowScript, we can see that our model was very similar to the actual experimental model. Based on this trend, they're very close together, and up until this point, and even here, they're not very far off. And this indicates that the GlowScript model that we constructed was a very good fit for the Tracker analysis. So what does all this mean? As we can see, the top of the slinky truly did stay stationary until the top part of the slinky fell on top of it, after which both parts moved together to hit the ground. The model we created in GlowScript did the exact same thing, then moved downwards, which can be seen from our graph. But why exactly does this happen? This is caused by the fact that the tension of the slinky pulling it upwards balances out the force of gravity until the whole slinky is compressed, after which the slinky falls. And we can take a look at the code again, and we can see how this is accounted for. So while the time was less than 5.44 seconds, that's when the top half of the slinky met the bottom half, and we accounted for the force of tension and the weight of the slinky. However, at this next point of time is less than 8.32 seconds, since the top and the bottom of the slinky were compressed together, we had to account for the force of drag combined with the weight force, as shown here by W, or as Fd and W respectively. So when we run this program, we can see that the bottom of the slinky stays stationary for a while, and then at some point it begins to streak downward because the weight of the tension can no longer balance out the weight of gravity, and the bottom of the slinky falls just like the top of the slinky does.